So I've mentioned in the past that a molar mass literally is the mass of 1 mole of whatever compound or chemical you're looking at. So here we're going to physically weigh out moles of different chemicals so we can visualize what moles truly look like in a physical setting. By the end of this video, you should be able to understand the entire concept, also visually and physically, of what a mole and atoms and molecules would physically represent in real space, and have a means of weighing out moles if you ever chose to do so. So first, I want to show you what 1 mole of the following chemicals looks like. What does 1 mole of water look like? What does 1 mole of table salt look like? And what does 1 mole of sucrose sugar look like? Now, just as a reminder, a mole is a huge number. 6.02 times 10 to the 23rd atoms or molecules is equivalent to a mole. That's a 6 with 23 zeros after it. That is a gargantuanly huge number. And I don't even know if gargantuanly is a word. If you remember the 1 mole of marshmallows analogy, if that was to fill the planet, remember that that would literally stretch 12 miles high into our atmosphere if there was 1 mole of marshmallows. So what does 1 mole of the chemicals look like? In this container, I have 1 mole of sucrose sugar. So this is what 1 mole of sugar looks like. Quite a bit of sugar, actually. 342 grams of sugar in this bowl. This is what 1 mole of salt looks like, NaCl, typical table salt. That's 58.45 grams of table salt. And this is 1 mole of water. That's 18 grams of water. Notice that the 18 grams of water is just in a shot glass, and it doesn't even fill up a shot glass. Whereas the other chemicals, like the salt, I needed this small glass here, but I needed an even bigger glass for a mole of sugar. So each chemical has a different gram amount of what is equivalent to a mole of it. So now that you've seen what a mole looks like, let's do some calculations using dimensional analysis, everyone's favorite, obviously, and figure out what different amounts of moles look like for the same kinds of chemicals. So for this little mini at-home lab that we're doing here, we want to know what the mass would look like for the following value of moles. So if I wanted to weigh out 2 moles of water, what would that look like? 0.02 moles of MgSO4, which is your Epsom salt, which is just plain old Epsom salt. If you've ever looked closely enough on the bag, it even says so right there on the bag, magnesium sulfate. Now, of course, weighing out this specific magnesium sulfate or Epsom salt is going to be just a little bit skewed because it has essential oils in it too, but it's pretty much the same thing. It's close enough. And it's what I had at home. I wasn't going to go buy a brand new bag of pure Epsom salt without any essential oils, because the essential oils smell nice. Come on now. Then we want to know what the mass of 0.1 moles of NaCl looks like and 0.3 moles of sugar. So in order to figure out the grams of this, we need to do some dimensional analysis. So right away you should note that we're given moles and the question is asking us for mass, and we know mass would be in grams for all things chemistry. So if we're given one thing and asked for another, we know we have to use our magical line to freedom dimensional analysis format. For the extra practice, go ahead and pause the video here and see if you can figure out the mass, the grams, for each one of these chemicals before I show you the answer for how to get there. Go ahead and pause now. All right, let's waddle right into these calculations. The first thing you should note is that if we were given moles and we're asked for mass, we're given MOL and we're asking for G. The only domino piece conversion factor that we have at our disposal is called molar mass. And molar mass is in units of grams per mole. How do we get molar mass? We have to look at our periodic table and we have to find where those atoms are, add up all the pieces for their individual masses to get the overall mass of the compound. So for water, we have 2 H's and 1 O. We need to look on our periodic table for H and for O. When we do so, we see that each H atom has a mass of 1.008, and there happens to be 2 of them. So 1.008 times 2 plus our water, and our water is 15.999, but I'm just going to round it to 16 to make our lives a little bit easier. And that gives us precisely 18.016 grams per mole. So now that's our molar mass domino piece for water. That's also the reason why there's 18 grams in this cup. There's 18 grams in this cup of water because that's equivalent to 1 mole. 18 grams per mole. 1 mole, 6.02 times 10 to the 23rd molecules of water exist in this cup. So remember, 1 mole of marshmallows, we all die as a civilization because they block out the sun and 12 miles into our atmosphere high. 1 mole of water fits in less than a shot glass. So now this question is not asking for just 1 mole, but asking for 2 moles. What does 2 moles look like? So we need to set up our dimensional analysis line. And this might be a little bit more intuitive for this one where you're like, oh, why don't I just multiply it? Because that's just 1 mole, so I just multiply it by 2. Yes, that's essentially what you're doing, but we're going to follow our same format setup as we have in the past. So we're always going to start by putting our given on the top of the line, our 2 moles of water. And where we're going, the goal units that we're going for is grams of water. What does that look like? And we calculated the molar mass of water to get there. We're going to plug that domino piece in here, our 18.016 grams of water in each mole of water. And then you can see, yes, if you intuitively already knew this, 2 times 18.016. And our moles would cancel from top and bottom and leave us with grams. So we knew we did this right. So our final answer would be 36.032 grams of water would be 2 moles of water. Let's see what that looks like. All right, as expected, the extra water, just times 2, filled up the rest of my shot glass with water. So this is what 2 moles of water looks like. 2 times the 6.02 times 10 to the 23rd molecules now exist in this shot glass. Prost! Ah yes, 2 moles of water were delicious. How about 0.02 moles of magnesium sulfate? That's our Epsom salts. So we're going to need to figure out the molar mass of magnesium sulfate before we can do our conversion. Let's start with that. We know that magnesium sulfate is composed of magnesium, that's here, sulfur, that's here, and oxygen, 4 of them, that's here. Let's write out each individual piece first. Mg, S, and then there's O4, there's 4 oxygens. We know from before that oxygen has a mass of 16 per oxygen atom, and there's 4 of them. If we look at our periodic table really closely, we can see that sulfur weighs 32.06. And if we look really closely again for magnesium, and magnesium is 24.305. All we need to do is multiply 16 by 4, which gives us 64, then add that with the other 2 values to get a total of 120.365 grams per mole of magnesium sulfate. So if I was to weigh out 120.365 grams on a scale of Epsom salts, that would be 1 mole of Epsom salts. But we're not interested in 1 mole of Epsom salts, we're interested in 0.02 moles of Epsom salts. So we still need to use our dimensional analysis setup. Let's set up our magical line to freedom and an equal sign with a space for our answer, and we're looking for grams of MgSO4. We're given 0.02 moles of MgSO4, and we want to know how much that weighs. So we're going to use our little dimensional analysis setup here for 120.365 grams per mole of MgSO4. And then we see that the moles of MgSO4 cancel and we're left with grams, which matches our goal unit. So huzzah, we got it right. Now all we have to do is 0.02 times our molar mass value of 120.365. So our final answer is 2.407. We need 2.407 grams of magnesium sulfate, Epsom salt. Let's see what that looks like. There is 0.02 moles of magnesium sulfate. It's beautiful. Now remember, if I was to weigh out an entire mole, I would have had to weigh out 120.365 grams. This is just 2.4 grams. How about the 0.1 moles of table salt? We still need to calculate the molar mass of table salt before we can do this dimensional analysis problem. So let's look at our periodic table and find Na and Cl. Na is right here, Cl is right there. Each Na atom weighs 23 grams per mole, and each Cl atom weighs 35.45 grams per mole. So when we add those 2 numbers together, 23 for sodium and 35.45 for chlorine, and there's only 1 atom of each in a molecule of NaCl, we end up with 58.45 grams per mole for NaCl. Let's set up our magical line to freedom. Our given is the 0.1 moles of NaCl, and we're going to try and find the grams of NaCl for that amount of moles. Going to take our molar mass, just like we did before, and plug that in, our domino piece, 58.45 grams of NaCl in 1 mole of NaCl. Then we see that our mole value cancels, and we are indeed left with grams, which matches our goal unit, so we did it right. Now all we have to do is multiply the 0.1 by 58.45. That gives us 5.845 grams of NaCl. I know you're just dying to see what that looks like. I know you know what a mole of salt looks like, but what does 0.1 moles of salt look like? Well, hang tight, I'll show you. Ta-da! There's our 0.1 moles of table salt, NaCl. Last but certainly not least, we have sucrose sugar. Let's find the molar mass before we do our dimensional analysis. We have 12 carbons, we have 22 hydrogens, we have 11 oxygens. On the periodic table, carbon is right here, hydrogen's over here, and oxygen's right there. Each hydrogen brings to the table 1.008, and there's 22 of them. Each carbon brings 12.011, and there's 12 of them. And each oxygen, as we saw before, brings 16 mass, and there's 11 of them. So that gives us 144.132 for the carbon, and 22.176 for the hydrogen, and 176 for the oxygen. These are all in grams per mole. These are all the total weight of that specific atom type. We need to know the molar mass of the whole compound, so let's add those three up together. And that gives us a final answer of 342.308 grams per mole of sucrose sugar. Let's set up our magical line to freedom. Magical line to freedom. Check. Our line for the answer. Check. And that's grams of sugar, C12H22O11 at the end of our line. And we need to plug in our lovely little domino piece, our molar mass, to end up with grams and cancel moles. So 342.308 grams of sugar in 1 mole of sugar. Here our moles cancel from the top and bottom, and we are left with grams. Again, we know we did it right, so let's multiply our 0.3 times our mass of 342.308, and we end up with 102.69 grams of sugar. And as before, of course I know that you want to know what 102.69 grams or 0.3 moles of sugar looks like, so drum roll. Ta-da! So, substantially less than the obviously 1 mole that we had before, because this is only 0.3 moles. It's not even half a mole of sugar. Y'all mold out yet? Hope not, because we're going to move on to something like aluminum foil, aluminium. We're going to figure out in this sample of aluminum the number of moles in this crumpled up ball that I just ripped off of some tinfoil, and the atoms that would be within this sample of aluminum foil. So in other words, we're going to be working backwards from what we were just doing. Before we had moles and we were trying to figure out what that looked like on the scale. Now we're going to have to take the mass of this and figure out, well, how many moles are in here and how many atoms are in here based off of its mass. Okay, so I'm going to weigh my aluminum foil now, and we'll see what, and we will use that mass to figure out the atoms and the moles. Turns out that clump of aluminum foil has 6 grams of aluminum. So basically our given in this scenario is 6 grams. We have 6 grams of aluminum crumpled up in a ball. So we'll draw our magical line to freedom, put an equal sign at the end, and figure out what our goal units are. The first goal unit here happens to be number of moles. So we want to write moles of aluminum. And we are given 6 grams of aluminum. So 6 grams of aluminum would go as the first thing on our line. To get from grams to moles or moles to grams, we always need to use our molar mass, which you need to look at your periodic table for. When you look at your periodic table, you see that it has 26.982 as its molar mass for aluminum. So we know that aluminum's molar mass is 26.982 grams per mole. As I said before, we also know that 6 grams is the amount of aluminum I currently have on my scale. Now we need to draw our dimensional analysis setup. So we need to draw our magical line to freedom, put the equal sign, a space for our answer, and then put the goal units at the end. Our first goal units is number of moles. So moles of aluminum. We are given 6 grams of aluminum. And from our periodic table, we saw that each aluminum atom brings 26.982 mass per mole with it. So we need to get grams canceled and moles on top. That means that this whole thing needs to flip-flop around. I need to put my 1 mole value on top, and I need to put my 26.982 grams on the bottom. Now the reason I do that is so that my grams here can cancel here, and I'm left with my goal units on the top. Now since I have one number over another number, technically I'm going to multiply 6 times 1, which just gives me 6, divided by 26.982. And that gives me 0.222 moles of aluminum in my 6 grams of aluminum on the scale. How about for the second question? The second question is asking us to calculate the number of atoms this time. So anytime we see atoms as the thing they want us to calculate for, you should be thinking Avogadro's number. Our domino piece would be the 6.02 times 10 to the 23rd atoms or molecules per mole. So that's the domino piece we'd have to use anytime we're asked about atoms or molecules. Let's draw our magical line to freedom, equal sign and a space for our answer. This time we're looking for atoms of aluminum in that clumped up ball of aluminum. And we know that it's still the same mass, it's 6 grams of aluminum. Now to get from the grams to atoms, I still have to use molar mass. Well, gee, I could have just kept the setup there from before, right? It's the same thing. I'm gonna have to get rid of grams, so I still have to flip this around, and then I'll end up left with moles. So I'd have 26.982 grams of aluminum in 1 mole of aluminum. That's the exact same setup we just did before. Now the difference is that I'm getting rid of my grams. I realize I'm still stuck with moles, which does not equal atoms. So we need another domino piece here, a second conversion factor to get there. Alternatively, you could have also just started with the 0.222 moles and used Avogadro's number from there, using the 0.222 moles as you're given. But I'm showing you the long way just for funsies. So now let's plug in our domino piece over here, 6.02 times 10 to the 23rd atoms of aluminum in 1 mole of aluminum. Now we see that the moles of aluminum cancel. I am now left with atoms of aluminum, which is what I wanted, so I know I did it right. Now multiplying across, I get 6 times 1 times 6.02 times 10 to the 23rd, all divided by this value, 26.982 times 1, which is just itself. So that's why we disregard it as we go. And we end up with an answer of 1.33 times 10 to the 23rd atoms of aluminum in this aluminum ball. I don't know, just take a minute to like revel in how awesome that is. That you just calculated the amount of moles and atoms of aluminum in this sample. Like literally you know how many atoms are in here of aluminum. That should blow your mind. It does mine, anyways. Now that I showed you how to do this with aluminum foil, I'd like you to try this iron nail application at home. I'm assuming most people have an iron nail at home, so if you've got an iron nail, find the mass of that iron nail on a scale. Hopefully you have some kind of kitchen scale or maybe a little scale like the one I have, the little mini one, or something like that. And find the mass of that iron nail, then calculate the number of moles that's in that iron nail and the number of atoms that would be in that iron nail. Additionally, I have this challenge question as your test yourself for this video. If you were to have, say, 5 paper clips, and I was to give you the mass of those 5 paper clips now, turns out that 5 paper clips weigh 5 grams. So since there's 5 paper clips and altogether they weigh 5 grams, on average, each paper clip weighs about 1 gram. So using that information, what would the mass of a mole of paper clips be? As an extra challenge, once you've calculated the mass of a mole of paper clips, then also write that answer in not only grams, but kilograms and pounds too. especially if you're from the States, because pounds are pretty much the only thing we use in the States, even though it's really not the best measurement of mass. But try to also calculate it into pounds using your conversion factors so that you have a better idea of how much that truly weighs to have a mole of paper clips. Post your answers in the comments below and I can check them, see if you got them right. If this video was helpful, please give me a quacks up and subscribe to my channel for more educational content and to reach more individuals like you who would enjoy this content or benefit from it as well. Hope your day is just ducky.
No ducks, no glory.